All right, welcome to this week's GOCC. We're very happy to have Jesse Kim from UC San Diego speaking. Before I introduce him, I just want to remind everyone of our community statement. So we have three sort of guiding principles. One is that we're all learning. The second is that everyone has something to contribute. And the third is that no one has all the answers. Okay, so today we're going to hear from Jesse Kim, who will be telling us about a Skein action embedding.
All right, thanks, Sarah, for the introduction. Yeah, so I'll be talking about a Skein action embedding. And so first I'll be talking about two different actions. So one will be a Skein action of the symmetric group on non-crossing matchings. The other will be a Skein action on non-crossing set partitions, and I'll tell you what all those mean. Then I'll talk about how to connect these two actions and why connecting these actions might be interesting, what the methods might lead to in the future. So the first action is going to be an action of the symmetric group on non-crossing matchings. So a matching is just a collection of disjoint size 2 subsets of n. And the way I'm going to be thinking about it is in terms of these diagrams here. So the lines on our circle are representing matched elements. So those are two elements in the same subset of n. So this matching on the left matches 2, 7. We've got 1, 4, and 5, 6. And the matching on the right has 2, 8, 4, 7, and 5, 6. A lot of the times, if you've heard the word matching before, you might require matchings to include all elements. So I'm going to be calling those perfect matchings. And a matching for me does not have to be perfect. So 3 and 8 are left unmatched. So matchings can either be crossing or non-crossing, and that's just going to be defined in terms of these diagrams. If two of the lines that we draw cross, it's a crossing matching. If none of them cross at all, it's a non-crossing matching. So this diagram on the left is crossing, diagram on the right is non-crossing. So if we think about the set of all matchings, the symmetric group, there's a natural action of the symmetric group on all matchings. And what you do is you just permute the vertices and then relabel them so they're in the correct order. So for example, if we act by the adjacent transposition 1, 2 on this matching on the left, what that does is it swaps the connection between 4 and 1 to be a connection between 4 and 2, and the connection between 7 and 2 becomes a connection between 7 and 1. So this matching on the left is sent to this matching on the right by the adjacent transposition 1, 2. If you prefer thinking in symbols, this is saying that two matched elements are sent to the matched sigma of A1, sigma of A2, if sigma is a permutation. But if you think about this action, it doesn't give you an action on the set of non-crossing matchings. Because if you start with the non-crossing matching and you act in this fashion, you could introduce crossings. Like if we started with the matching on the right and acted by this same transposition, well, that's going to have to just be sent to the matching on the left, and that's suddenly there's a crossing. So this natural action, we don't get an action on non-crossing matchings. But what we can do to fix this is think about linearizing. So instead of acting on just the set of non-crossing matchings, we can instead act on the vector space spanned by non-crossing matchings. So if we allow the image of this action to be like sums of matchings, we can actually get an actual action on non-crossing matchings. So the way that's going to work is via this relation called a Ptolemy relation or a Skein relation. So that's where the word Skein is coming from. That says if you have two edges that cross, you can replace them by both ways to connect those 4 elements, to pair up those 4 elements in a non-crossing fashion. So we can either pair up the top 2 and the bottom 2, or we can pair up the left and the right. And this relation actually shows up a bunch of other places in math, like in knot theory. A very similar diagram is used to think about. So there's a question in the chat: is the set of Ptolemy relation a poset? I'm not entirely sure what you mean, because I'm just thinking of this one relation. But yeah, it shows up in other areas of math. So there's like in knot theory, and also the Plücker relations. They look like this. If you think about calling these like A, B, C, D, you can think of the matrix minors AD and BC being equal to AB, CD, etc. So the way this action is going to be defined is okay. So if you think about like changing which vertices you're using, you get a set of Ptolemy relations. And can you give that a partial order? I haven't actually thought about that. So I don't know, maybe. If someone else knows, they can answer. All right, so the way this action is going to work is that we first are going to act as before by just permuting vertices, but that might introduce crossings. And so what we're going to do is use this Ptolemy relation to get rid of these crossings. So for example, if we start with this matching where 2 and 3 are matched, 1 and 4 are matched, 5 and 6, 7 and 8, and we act by 2, 7, 8. So that's going to send this 3, 2 to 3, 7, and it's going to send 7, 8 to 2, 8. So we've got two crossings, and what we're going to do is take this first crossing, 3, 7, and 1, 4, and get rid of it using the Ptolemy relation. So 3, 7, 1, 4, we're going to match up 1, 3, 4, and 7 in the two ways that make them not cross. And then we still have we have one crossing remaining in each of these diagrams. So we're going to apply the Ptolemy relation again to both of these, and we'll end up with a sum of 4 matchings. So the action of 2, 7, 8 on this matching here gives us the sum of these 4 non-crossing matchings. Yes, it is. And the way to see that, so the question in the chat was, is every matching equivalent to a sum of non-crossing matchings modulo the Ptolemy relations? And the answer is yes, it is. And the way to see that is because every time you apply one of these Ptolemy relations to get rid of a crossing, the total number of crossings in your diagram will go down. So if you apply it enough, you're going to have to end up with 0 crossings.
Does the order
matter? Sorry, what was that?
Does the order matter? Like they were like you kind of.
That's actually a great question, right? Because we could have also started with taking the crossing 2, 8 and 1, 4. And it turns out that the order doesn't matter. So if you go in the opposite direction, if you start with this crossing here, you end up with the same sum of 4 terms. And yeah, checking the braid relations is exactly how you can show that the order doesn't matter. If you think about what happens within an individual adjacent transposition, you can show that if you work out what those do and work through the braid relations, you can verify that. All right, so that's how this first action works. And so this action is not new. This is pretty classical, I think. I don't actually know where it first shows up, but I'll go to some examples of where it's been shown up, where it's shown up. All right. So if we focus instead on perfect matching, so that's matchings where everything is matched. So this one on the right is perfect because every vertex is connected to something else. The one on the left is perfect. The one on the right is not perfect because 1 and 3 are not matched. Perfect matchings form an invariant subspace in this action, because if you think about what this action is doing, it's not changing the number of matched pairs. So if there are n/2 matched pairs, if you apply this action, you're still going to have n/2 matched pairs. So perfect matchings form an invariant subspace. And it turns out that that subspace is irreducible. And it turns out to be isomorphic to the spect module for a 2-row rectangle NN. And so the spect module NN is one way of defining the irreducible representations for the symmetric group. The standard basis for this spect module is using standard Young tableau. But standard Young tableau are not super nice in terms of, yeah, that's where I know it from, Stefan, but I don't know if it appeared earlier as well. So standard Young tableau are not super nice in terms of symmetry properties. If you try to act by a permutation on a standard Young tableau, like there are rules for doing it, but it's often not super nice. And this action turns out to be a lot nicer, because if you think about acting on a perfect matching, if you act by a rotation, so if it's like a cycle that permutes all the elements, you end up not introducing any crossings. You're just rotating this diagram. So a rotation of a perfect matching gives you another perfect matching. So it's particularly nice in that way. If you act by any rotations, any reflections, you end up with just another basis element rather than a sum of basis elements. So that's why this matching might be more interesting than the Young tableau basis for the spec module SNN. Yeah, so it shows up in a variety of places. So SL2 webs is the paper that Stefan mentioned in the chat by Cooperberg. It's also an example of Kazhdan-Lustig cells, which I'm not super knowledgeable about myself. And there's also some applications to cyclic sieving. So you can have a cyclic sieving result on non-crossing perfect matchings. And this is one way to prove that it works out. All right. So that's the first action that we're going to be thinking about today. And I can talk more about these topics at the end if there's time. The second action we're going to be thinking about today is similar, but it's an action on non-crossing set partitions instead of matchings. So non-crossing set partitions we're going to be thinking about using similar diagrams to matchings. So it's essentially the same thing, except now your paired elements can have more than 2 things in them. So this set partition on the right, we have one block that's 1, 3, 4, one block that's 2, 7, 8, and one block that's 5, 6. It's crossing if, when you draw it out like this, 2 of these polygons intersect. So this one on the left is crossing, one on the right is non-crossing. And so this action was introduced in, I think, 2015 by Brendan Rhodes, my advisor. And so the way this action is going to work is going to be similar, except we're going to need multiple relations. So we're going to need, these are called Skein relations, and these are analogous to the Ptolemy relation that was used to define the first action. And the way these relations work is that they depend on the sizes of the blocks that cross. So if you have 2 size 2 blocks that cross, so that's basically the same as the matching case, we're just applying the Ptolemy relation. If you have a block of size more than 2 and a block of size 2, you get this extra term here, which takes the 2 vertices that cross and sticks them together along with the third vertex from your size 2 block. And if you have 2 blocks of size more than 2, you get 2 new terms. So the way this action is defined is then is similar to the matching action, but we're first going to just define it for adjacent partitions. So if we look at this diagram on the bottom, the way this works for adjacent transpositions is that you swap the 2 elements in your adjacent transposition. So if we're acting by the transposition 6, 7 on this matching, on this set partition on the left here, we swap 6 and 7. And now we have these two blocks that cross in a similar way to one of these rules on the previous slide. So they cross, we've got a block of size more than 2 and a block of size 2. So we'll apply this middle rule to uncross these blocks. And we end up with this sum of 3 non-crossing set partitions. Then to do this in general for any permutation, you first write your permutation as a product of a bunch of adjacent transpositions and apply this adjacent transposition rule to each of them. So that's why these 3 non-crossing rules are all we need, even though in the set partition world, blocks could potentially cross in much more complicated ways. Like you could have a block that crosses this here and then crosses it again over here and comes back here. But if we only think about doing one transposition at a time, if we start non-crossing, apply a transposition, we can only get blocks that cross in one of these 3 ways. So that's why these 3 rules are enough.
And so just a quick question on that previous
Yeah.
slide. The way we colored these blocks is we gave different colors to vertices on different sides of the crossing.
Yeah, so these are the vertices that got swapped by your adjacent transposition.
Oh, okay. Those are just adjacent vertices, not.
Yeah, those are adjacent vertices. Yeah, I should have clarified that. So this question in the chat, is there an analog of this for ordered set partitions? So not that I know of. It's possible that you could just keep track of the same order on blocks. Although there's issues there if you think about like the second relation, like this term of the second relation here, if you had like an order on the blocks here, how would you say which order these blocks should be in this second relation here or this third relation here? So I don't know if you can turn this into an action on ordered set partitions because of that reason. But it might be possible. So it's a good thing to think about, definitely. All right. So yeah, so that's how this action works. And it's been found sort of in the wild in a few places. So myself and Brendan, we found it as part of the top degree piece of a variant on the diagonal coinvariant ring, if you're familiar with that. It's also been found via invariant polynomials by another group. So they found a set of invariant polynomials that if you assign a non-crossing set partition to a specific invariant polynomial, the natural action on polynomials matches this action on non-crossing set partitions. So that at least gives some evidence that it might be worth studying. But yeah, so where do these uncrossing rules come from? Because they're sort of, how did you come up with these? Why should we care about these specific rules? Is the question. And so I asked Brendan about this. And the reason he thought to look for these is because there's a cyclic sieving result on non-crossing set partitions. So he expected that there should be an action that extends the cyclic action on non-crossing set partitions to the entire symmetric group. So he decided to just look for it, and he just sort of played around with various relations like these until he found one that worked. In order to check that they work, what you can do is you check the braid relations, as was mentioned earlier in the case for matchings. You just check that if you apply the adjacent transposition SI, then SI plus 1 SI, you get the same thing as doing it in the reverse order. Although this task is pretty extensive, there's some high number of cases in the 20s or 30s that you have to check because of various ways that you could apply these different relations one after another. So the question that I'm going to be trying to answer for the rest of the talk is there a better answer to where these uncrossing rules here are coming from? Is there a way to find them without just guessing them? And so the way we're going to think about that is by first we're going to think about what the module structure of this set partition action looks like. So if you think about the set partitions with a fixed number of blocks and a fixed number of singleton blocks, that gives you an invariant subspace. And the reason for that is because none of these uncrossing rules change the number of blocks. None of them introduce or remove singleton blocks. So, and that's sort of why there has to be 3 different ones. If we try to add on one of these terms that appear in the later ones to this first relation, you'd end up with a block of size 3 and a block of size 1. And that would create a problem for reasons that I'll try to explain later. So that's why these extra terms are missing from these previous ones. So when you think about set partitions without any singleton blocks, so the number of singleton blocks is 0, you actually get an irreducible subspace. And it turns out it's isomorphic to the spect module, where you have 2 rows of length k, and then a bunch of 1s to fill in the rest. And k here is the number of blocks in your set partition. So that looks pretty similar to the spect module that we had for matchings. I'll remind you that was just 2 rows of the same length. So we've got 2 rows and we've got a bunch of extra 1s. So it turns out that we can actually add on all these extra 1s in the matching case. So if you think about, rather than perfect matchings with exactly k pairs, we can also figure out what that's going to be isomorphic to. And the way we can do that is by thinking of a matching with exactly k pairs as a perfect matching on a subset of the vertices, and then a bunch of floating singletons that we think of separately. So the way you act on this, this matching here is, well, part of your permutation is going to tell you about what you're doing with the perfect matching on the 4 vertices 1, 2, 3, 5. Part of your permutation is going to be telling you about what you're doing with the singleton vertices, which is nothing except introducing a sign based on the sign of your permutation. I think I forgot to mention that. Yeah, sorry. Let me go back a few slides. So in the matching case, this acting by the matching also introduces a sign based on the sign of the permutation. So in this case, it didn't, because 2, 7, 8 is an even permutation. But if this was an odd permutation, we'd get a negative sign here. So back to this slide. So part of your permutation is telling you about how you're changing your perfect matching. Part of it is just giving you a sign. And part of it is telling you how you're swapping which vertices are in your perfect matching and which vertices are singletons. So that's exactly how an induction product works in algebra, right? This is the induction from the product of the symmetric group on the vertices 1, 2, 3, 5, and the product of the symmetric group on the vertices 4, 6, 7, 8, to the symmetric group on all vertices. And because the singleton vertices are just being a sign representation, there's a nice formula for what the isomorphism type of this representation is going to be. That's the dual Peary rule. So we're taking a product of a representation that is isomorphic to a k by k, or a 2 by k rectangle. So we've got a row of k and a row of k, and we're multiplying it by a sign representation, which corresponds to a column. The Peary rule tells us that this breaks down as a sum of irreducibles, where we add one element to, or we add 3 elements all in different rows. So we can either add them in the first, second, and third row and get a k plus 1, k plus 1, 1, or we can add 1 in the first row and 2 in the third and fourth rows. And so we get a k plus 1, k, 1, 1, or we can add them all at the bottom in a column. And that gives us our k, 1 to the n minus k shape. So in this match, in the invariant subspace generated by matchings with exactly k pairs, this representation S k, 1 to the n minus 2k appears exactly once. So what that means is that by Schur's lemma, we've got the action on non-crossing set partitions with exactly k blocks and no singletons. That's an SKK 1 to the n minus k. And this action on matching with exactly k pairs contains exactly one copy of SKK 1 to the n minus k. So Schur's lemma tells us that there has to be a unique embedding of this first span into the second span. And so that actually has a nice combinatorial description. So let me tell you about what the combinatorial description of that is. So the way this map works is that you take your non-crossing set partition and you think about all ways to pick a single matched pair from each block. So we've got 3 blocks. We've got a block 2, 3. We've got a block 1, 4, 8. We've got a block 5, 6, 7. So we always have to take 2, 3 because there's only 2 elements there. So we take 2, 3, and then we can either take the pair 1, 4, 4, 8, or the pair 1, 8. And then from our last block, we can either take 5, 6, 5, 7, or 6, 7. So we've got 3 options for block 1, 4, 8, 3 options for block 5, 6, 7. So we get 9 total matchings that come from selecting one pair to match from each block. And this non-crossing set partition on the left is sent to the sum of all 9 of these matchings. So yeah, so that's how this embedding works. And using this embedding, you can actually see why these uncrossing rules from earlier are the way they are. So if you think about what each of these set partitions is sent to, they're sent to all ways to take, well, we have to take this matched pair, and then we can take any one of the 6 ways to match 2 of these elements. And the way we can see that this is going to be the right relation is to think about selecting 4 vertices and focusing on what matchings using them appear in each of these terms. So if we focus on just this vertex, this vertex, this vertex, and this vertex, the only way that those can be matched up in the image of this non-crossing set partition on the left is, well, these 2 have to be matched up and these 2 have to be matched up. So we just get this one term. If we think about those same 4 vertices on this second non-crossing set partition, these two have to be matched up, so these two have to be matched up, and we get this one term with a negative sign. And if we think about this third one, well, these two are going to have to matched up, and these two are going to have to be matched up, so we get this one term. And this fourth one, we have these 4 vertices that we're thinking about. So this vertex doesn't have a partner it can be matched to. In the image of this set partition, it can only be matched to one of these 2 vertices. So this contributes nothing to matchings with those 4 terms. So what you get is just a Ptolemy relation when you focus on these 4 matchings. If we instead focused on 4 vertices like these 2 here and these 2 here, then this term would contribute one matching like this and this. This term would contribute nothing because this vertex cannot be matched with any of these 3. And this term would also contribute nothing because this vertex cannot be matched with any of these 3. But this final term would contribute the same matching as the first term, so we again have equality. So if you think about the image of this under that map that I described earlier, what you get is just a sum of a bunch of Ptolemy relations, as well as equal things that cancel out on either side. So we can think of the, I guess I've also extended this action to all set partitions. I should have said that earlier. So sorry, I extended this map to all set partitions. So it's no longer embedding if you extend it to all set partitions. It was only an embedding on non-crossing set partitions. So when you extend it to all set partitions, you get a kernel. And the kernel is exactly generated by the uncrossing rules from before. So if you didn't already know the uncrossing rules from before, what you could have done is thought about the kernel, looked for simple generators of it, and hopefully you would then find these 3 terms. I'm not entirely sure how easy it would be to just given this algebraic kernel find simple generators for it that look nice, but it's a possibility at least. Yeah, so that's the idea behind these 2 matchings and how they're connected. And so the reason that, or one of the reasons that I wanted to think about this is because it'd be nice to be able to create new actions in a similar fashion. So both of these actions were already known. I was just thinking about how better to link them. But the hope is that if you had some SN action on that for an irreducible representation that was more combinatorially nice than the standard Young tableau basis, perhaps you could perform some similar ideas to convert that basis to a basis for the same shape with an extra tail of 1s added as an extra column. And so one possibility I've been looking at is something called SL3 webs. So an SL3 web is a bipartite planar graph embedded in a disk with 3n vertices on the outside of the disk. All of the interior vertices have degree 3. There's no cycles of length 4 or 2. And we're thinking of the disk as not connecting these vertices. So the vertices on the outside are degree 1. They're just connected to these. And the boundary vertices are all in the same part of your bipartition. so this should say no cycle of length 4 or 2. Apologies on that. And SL3 webs, there's a similar way to define an SN action that gives you a module isomorphic to 3 rows of equal size. So a spec module for the partition KKK. I probably shouldn't use K there, but yeah, so SL3 webs give that. And it's not too hard to see how to introduce an induction product structure here. You can just introduce floating boundary vertices that are not connected to anything. So if you have n boundary vertices and you connect 3k of them with an SL3 web and use the same sort of action that applies to SL3 webs, you get an induction product of a 3 by k rectangle and n minus 3k, a column of n minus 3k ones. So that, again, with the dual PRU rule, will have exactly one copy of S, a 3 by k rectangle with the tail of ones. And so if you want to understand the structure of a 3 by k rectangle so if you want to come up with a combinatorial basis of a 3 by k rectangle with a bunch of ones, then you can try to find that irreducible component of this module and try to understand or try to come up with a combinatorial basis for that. So that's one hope for future directions that I have. And I think there's some promise because I've been able to find a set that has the right structure, although I haven't been able to actually give an action of SN on it. So it turns out that, well, this is still a conjecture, but it turns out that through experimental evidence, it seems like if you take this definition for SL3 webs and you change this interior vertices condition, all being degree 3, to interior vertices in the same part as the boundary vertices are degree 3, but interior vertices in the other part, so these white vertices, can be any degree at least 3. The number of ways to draw that it turns out to be equal to the dimension of this module. So it seems like there's a good chance that there is some action you can put on those. Yeah, the idea there is that you could maybe try to send, if you attach like an extra vertex here, you could maybe try to send that to the sum of all ways to sort of pick three edges on this white vertex to keep and one to throw away. That idea doesn't quite work out. So maybe there's some refinement of that idea that would, though. So yeah, so that's yeah, so that's the idea of where I'm trying to go with this. And actually ended a bit early. But thanks for coming. So I guess we can go to questions early.
Let's thank Jesse for the great talk. Okay, yeah, so we have lots of time for questions if anyone has any. Does anyone have questions?
I have kind of my immediate question is when you kind of came up with this embedding, you said you could use the kernel to generate these, I guess, I don't know what you call them, generalized Ptolemy relations,
Yeah, so
uncrossing rules.
I call them uncrossing rules here. They're also called Skein relations.
Okay,
Yeah.
but these are just skein relations for transpositions. Is there a way to use your more general understanding to get the uncrossing rule for uh larger permutations?
Yeah. So actually, in the paper that found this action in the variance of the diagonal covariant ring,
Right.
we were able to use that action to give a description of what the general uncrossing rules is. It's kind of complicated, so it's a big sum of like all ways to, so you break up your two crossing blocks into all the parts that are consecutive along the
Okay.
circle.
Mhm.
So if you had like two triangles that cross like this, you'd break it up into the points here, the points here, the points here, points here, points here, points here. And you then think about all ways to combine those 6 parts into 2 blocks. And then there's some signs that depend on the sizes of those blocks and how many are being combined. So that's what the general uncrossing rules look like. And yeah, I think you should be able to find them in the kernel.
Okay,
Yeah.
thank you.
Is there a reason that you're interested in like the doing like a vertical strip instead of a horizontal strip or something? Or is that just like you could do the same thing but unsigned?
Yeah, I think you can just do the same thing. But you won't be acting by a sign.
Mm-hmm.
I don't have a good reason why thinking that you including the sign would have a better chance,
Mm-hmm.
but I sort of feel like it will, just from examples, but I don't have a good reason for thinking that.
Okay. Interesting. Any other questions?
It looks like Stefan's audio isn't working currently, but he appeared to have a question.
We can't hear you.
Huh. Da. Can you
No.
hear me now?
Yeah.
Okay, I only need to click the open settings button and then it works. Okay. So my question was, there was a paper by Chris Fraser earlier this year, finding the diagrams for the rectangular 2-column arbitrary many rows basis, more or less. Have you had a look at this paper? And
I haven't had a look at that, but that's definitely something I should check out. Yeah, thanks for telling me about it.
And I also have some good news. We probably have a basis for SL4, but it's still work in progress to write that out.
Nice. Yeah, well, once that comes out, I'll have to take a look at that as well.
Can you remind us what the, I think you said this, but like what the connection is with the co-invariant ring? Or like the variant of it?
So if you take a polynomial ring with 2n anti-commuting variables,
Mm-hmm.
and you So you can act by the symmetric group on that, such as by permuting each so you have n variables of one type, n variables of another, and if you permute those n variables simultaneously, you can act by the symmetric group on that. If you then quotient out by the invariant SN invariant polynomials, you get that the top degree is also isomorphic to this module. And so we were able to find a basis using polynomials in that ring that had the same action. So I didn't really say much in the talk, but I can also point you to the paper if you want.
Is there a connection for the other degrees? Or like anything that you know? Connecting this to
The other
lower
degrees, there's some combinatorial interpretations of other degrees that we found, but they weren't as nice and they aren't directly connected to this particular action.
Okay. Cool. Okay, any other questions? Okay, let's thank Jesse again. Yeah, that was a really nice talk. I really liked it.
Thanks.
Very